So the first question that is asked is, there's a problem which we looked at as a practice problem. It's problem 3.11 in the text. And the problem asked to compute the DTFT of the unit step function, so u of n. Okay. And if you look at the solution manual that is provided to you, they go about various tricks to try to compute this DTFT, and all of those steps should be pretty clear to you. So the main question that was asked is, why can't we just use the definition of the DTFT in the case of unit step? And the answer is the following. The formula for DTFT should be used only when you satisfy the condition that we looked at for convergence of the discrete time Fourier transform. So the condition for convergence of discrete time Fourier transform of a sequence xn, that condition is that if you sum all the entries, take the square of their absolute value, that should be less than infinity. Okay. So if you look at, of course, un is an infinite sequence that goes from 0 to infinity. Each of its value is 1, so of course it does not satisfy this condition. And whenever a sequence does not satisfy this condition, we have to play certain kinds of tricks. In some cases, you can use those tricks to get some sort of a discrete time Fourier transform. In other cases, you may not be able to. Okay, so like cosine is another example. Cosine is a periodic signal. It keeps on varying. It does not satisfy the condition. But we can get to its Fourier transform through using this complex sinusoid expression and sort of going about it in a reverse fashion. So the way this problem is solved in your solution is the author expresses this in terms of delta functions. And since we know the discrete time Fourier transform of the delta functions and the constants, he's able to show that the DTFT of un is equal to 1 over 1 minus e to the minus j omega plus summation k from minus infinity to infinity pi of delta omega plus 2 pi k. Okay. You can go through the steps personally, but that is one of the reasons. If you don't satisfy this condition, then you should never try to take the sequence and plug it into the DTFT formula. So the next question that is asked is, what is the difference between a continuous time sinc function and a discrete time sinc function? Well, one of the primary differences that one is just a function of continuous variable and the other is a function of discrete variable. Now, continuous time sinc function let's call that x of t, that is given by sine pi t over capital T over pi t. So if I take the Fourier transform of this sinc, let's call that x of j omega. The Fourier transform is a low-pass filter, if you want to think of it. It looks like this box function with a cutoff at pi by t and minus pi by t and a height of 1. So this is a sinc function. If it is given by sine pi t over capital T, pi t, whatever is the expression here, this pi over t is the cutoff. for the low pass filter. So sometimes you will also see it as sine of omega ct over pi t. Well, the Fourier transform of that is simply, again, a box function with cutoff of omega c with a height of 1. So if you are talking about low pass filters in continuous time, with the standard low pass filter, which is the height is 1 and the cutoff is omega c, the impulse response of that filter is this expression, sine omega ct over pi t. And in time, this thing looks like it has this kind of a shape. Now let's talk about another version of this. Let's call something x1t, which I call t times x of t. Okay? So if I scale something in time, what happens to that function's Fourier transform? So if I multiply x of t with t and I say let's calculate its Fourier transform, it turns out that the Fourier transform of x1 of t will simply be equal to t times Fourier transform of x of t. Okay? Which means that the Fourier transform, if I multiply my standard sink with capital T, the Fourier transform will look like still the same shape, omega c minus omega c, but now the height, instead of 1, it will be capital T. Now let's look at what does this thing look like. This will be sine pi t over capital T over pi t, and there's a t multiplier here. Well, I can equivalently write that as sine pi t over capital T over pi t over capital T. Okay. So in our course when we did, this is the typically this is how our anti-aliasing filter looks. Our anti-aliasing filter is typically has a cutoff of pi by t, but anti-aliasing filter is not supposed to scale any frequencies. It just keeps all the frequencies at 1. So the impulse response of our anti-aliasing filter is given by sine pi t over capital T divided by pi t. Now our reconstruction filter looks like this. This is typically how our reconstruction filter looks. It has the same cutoff, omega c equal to pi over t, minus omega c equal to minus pi by t. But the amplitude of this reconstruction filter is capital T, and that's why its inverse Fourier transform or impulse response looks like this. Okay. When we talk about sink interpolation, we use this expression in sink interpolation, because sink interpolation is really about using the impulse response of your reconstruction filter. Now if we go to the discrete time sink, the discrete time sink has a very similar formula. Let's call it xn. Okay. That is similar to the continuous time sink. It is given by sine. So the continuous time one was given by sine omega t, capital omega, where we took that to be pi over t. The discrete time sink is given by sine little omega c n over pi n. Okay. So compare this to the continuous time, which had x of t equal to sine capital omega ct over pi t. Okay. So it's the same expression. Now if you plot it, actually what it turns out is that the discrete time sink is nothing but samples of your continuous time sink. So let's say if I was doing sampling of this by, I call it t equal to nt. Then I get x of n equal to sine of omega c nt over pi nt. And so I get sine of omega ct times n over pi n, and I get a factor of 1 over t. Right? So this part is what you can think of it as your discrete time sink. Okay? Your discrete time sink, if you plot it, it looks like its envelope is very similar to the continuous time envelope, and then it does the same kind of expression, but it's now in discrete time. And if you take inverse Fourier transform of this thing, or Fourier transform of this thing, the discrete time Fourier transform, you get x of e to the j omega, which is, so the continuous time sink has a Fourier transform which looks like a low pass filter. Well, the discrete time sink also has a Fourier transform which looks like a low pass filter, but in discrete time, of course. So it's a discrete time low pass filter. So its frequency response looks like this. Minus pi, pi. It has a cutoff of, in the continuous time, it had a cutoff of capital omega c. In the discrete world, it has a cutoff of little omega c. And then you have the periodic repetitions. Okay? And the height of this is 1. So the relationship between them, they are sort of dual of each other. The continuous time sink has a Fourier transform which looks like a low pass filter. The discrete time sink has a Fourier transform which is a low pass filter. Their shape is very similar. Of course, the discrete time sink has these impulses rather than a continuous envelope. The comment I was making about the normalization is the following. Let's say that if you have learned to define sink of t as sine pi t over t or pi t. If that is your common definition of sink, now I wrote earlier x of t equal to sine of pi t over capital T over pi t. So I can just multiply and divide by a capital T in the denominator. Right? So what do I get? I get then 1 over t sine pi t over capital T times pi t over capital T. And if this is your definition of a sink, that whatever is the argument of sine has to be the same in the denominator, then you will say this is just equal to 1 over t sink of t over capital T. Okay. So it's just a normalization factor, and if you have learned this sink has the advantage, if you have learned that this sink basically its amplitude is 1. Well, because of this 1 over t factor, it is saying your amplitude now will be, instead of 1, it will be 1 over t. Okay, so the next problem is problem 5C in practice problem 3, practice set number 3, where you are given a time domain signal and you are asked to evaluate minus pi to pi x of e to the j omega d omega without explicitly computing the discrete time Fourier transform. Okay? So we are given x of n in terms of its real part and its imaginary part. Okay? Now, how do you get that? Well, remember the definition of xn. Right? Xn is defined as 1 over 2 pi minus pi to pi. So I'm just writing the definition for the inverse Fourier transform. Right? Minus pi to pi e to the j omega n d omega. So if you compare, we are interested in evaluating this part, right? And we are given xn's. So if you compare the two, what is the difference between the two? The only difference is that there is this additional e to the j omega n factor. If this e to the j omega n was 0, if this e to the j omega n was 1, will be done. Right? So how do we make it this e to the j omega n 1? Well, if n equal to 0, this means that e to the j omega n equals e to the j omega 0, that is equal to 1. So for n equal to 0, I have that x of 0 is 1 over 2 pi minus pi to pi x of e to the j omega d omega. So if we are interested in now computing only this part, what do we do? Well, that is equal to 2 pi x0. So the next question that is asked is about this confusion with when do we have the change of scaling when we go from continuous time to discrete time or discrete time to continuous time. Okay. So, and that is one of the fundamental concepts that you should have a good grasp of, especially for the exam, but in general too. So here is the setup. You have a continuous time signal, g of t, and you do continuous to discrete, and you get g of n. Now, if I give you the Fourier transform of this g of t, and you are given the Fourier transform as g of n, the question is, how are they related? Okay. The scaling factor that we talk about, 1 over t, or all the sort of scalings that we talk about in the class, we have always done them in the frequency domain. So first of all, you need to go to the frequency domain. Okay. So you can't say Gn and Gt are related by any scaling of the amplitude. It's really their Fourier transforms. Okay. Now the relationship, the way we went about it is we actually had an intermediate function which we call Gpj omega, which was defined as Gp of t was defined as summation of n equal to minus infinity to infinity g of n delta of t minus nt. I think some of the confusion about when to do the scaling of the amplitude perhaps comes from when we go first to this Gp and then to Gn. So I'm going to, in this discussion, skip that intermediate part. If you want me to talk about that, I can come back to it later. Okay. The general principle is if your g of j omega, okay, once you go to the frequency domain, this is, let's say, your transform. Let's call this omega m minus omega m, and the height is a. Then the relationship of the discrete Fourier transform g e j omega is given by 3 specific operations. Number 1, there is a scaling of amplitude of the Fourier transform always. When you go from discrete, continuous to discrete, there is a 1 over t factor. Okay? It's not a question of when we have it or when we not. We always have that factor. And then you get scaling of the axis. You get g of little omega over t. Okay. So that is the other thing you get. You get a scaling of the frequency axis. So you have scaling of the amplitude, you multiply it by 1 over t, and you have scaling of the frequency axis. You go from radians per second to radians by multiplying by t. And finally, you get repeated copies every 2 pi, multiple of every 2 pi interval. So you have minus 2 pi k here also. Okay? And the way it looks is you are first going to scale the main copy at 0. So this is capital omega axis. Now you are in little omega axis. The height gets scaled by a over t. And then this gets omega m capital T. This gets minus omega m capital T. So the frequency axis gets multiplied by capital T. And then there is a periodic repetition of that at 2 pi, at minus 2 pi, and so forth. Now whether the repetition will overlap with your main copy will depend upon whether you satisfy the Nyquist criterion or not. Right? Whether this point, omega mt, whether this is bigger than m or bigger than pi or smaller than pi. Right? Because if omega mt is less than or equal to pi, if and only if omega m is less than or equal to pi by t, which is the Nyquist criterion. Right? So let's assume that you did satisfy the Nyquist criterion, then you would get this picture. Okay? So this is the relationship of going from continuous to discrete time. So now when we talk about this, the confusing part that sometimes throws people off is, let's say that my g of t was made up of impulses in the Fourier domain. So let's say my g of t was cosine of omega naught t, in which case my Fourier transform is g of j omega equal to pi delta of omega minus omega naught plus delta of omega plus omega naught. If you plot them, of course, you'll get two impulses, one at omega naught with an area of pi, one at minus omega naught with an area of pi also. Now, what gets confusing sometimes is, in the solutions perhaps what you have seen is that if I plot GE of j omega for this, the way I will plot it is I will get an impulse, so there will be scaling of the frequency axis. I'll get an impulse at capital omega naught t minus omega naught t. Let's say this is pi minus pi. You satisfied the Nyquist criterion. And then I'll have the same repeated here around 2 pi, around minus 2 pi. And the question that was asked was, we just talked about there is always a scaling of the magnitude. So if you look at your solutions, though, the solutions still show pi. Where did 1 over t factor go in this case? And the reason the 1 over t factor disappears in this case is because you have the property of the Dirac delta that if you scale the axis of the Dirac delta, you get an additional factor. This was one of the problems in your homework. The idea is that delta of x is defined not through its value, but through its area, right? If you remember your technical definition of delta of x, it is that it is equal to 0 for all x not equal to 0, and the integration from minus infinity to infinity of delta of x dx is equal to 1. That is the mathematical definition of delta x. So one of the problems you were given was that if you scale your delta x by delta x over a, what is that equal to? And the answer is that is equal to 1 over a delta of x. So the reason there is no pi factor here is there is actually, in reality, what happens is that when you go from here to here, there is a 1 over t factor due to the scaling of the magnitude. But then you also scaled the frequency axis by t. And so you get an additional factor of t due to that scaling, which is due to this property of the impulse. Okay, so those t's cancel and you end up with the same area. Okay, so what we talked about earlier is still happening, but since you are now changing both the amplitude of your impulse and also changing its axis, you're scaling its axis also, you have to account for both of them. And for that, you have to really pay attention to this property of Dirac delta. Okay. Which is not the case if you did not have a Dirac delta. So the next question that is asked is about phase of the Fourier transform of a function. Of a signal which could be discrete time or continuous time. So I'll take the example of just the discrete time Fourier transform. The idea for continuous time Fourier transform is pretty much the same. So what you have x of e to the j omega, the reason this notation is so great is what this says is that the variable in this Fourier transform is little omega. So for every value of little omega, you have some number. Right? So the discrete time Fourier transform is really for every value of little omega, it is giving you a number. Now this j is meant to signify that in most cases, the Fourier transform ends up being complex. So you get a complex number, not a real valued number in most cases. Okay? And why we have E to distinguish it from the continuous time Fourier transform. So in the continuous time Fourier transform, we have x, j, capital omega. Of course, whether you use capital omega or little omega, that is just a dummy variable. So that's why they use e to the j to signify it is discrete time Fourier transform. They use just j to signify its continuous time. J is meant to signify that for every value of little omega or capital omega, you get a complex number. Now, when we are talking about a complex number, so that is a plus jb, the general form. It has a real and a complex part. That complex number has a phase and a magnitude associated with it. Basically, what we have is we can write this complex number as r e to the j phi, right? Where this r is bigger than 0, so it's a positive number. And what this is saying is that this complex number is at a length of r away, and it makes an angle phi with this x-axis, right? So you can also compute. We know how to compute r other ways. It's a squared plus b squared square root, right? And phi is simply tangent inverse of b over a. So now if you are given, let's say x of e to the j omega, which is a complex number, the goal is that you want to represent your x e to the j omega in this form. Okay? You want to write it in terms of some positive value number for each little omega. So what we typically write it as x of e to the j omega absolute value, e to the j angle of x of e to the j omega, where this is just, you can also write it as phi of omega. Okay, so once you write it as a function of little omega, just treat it as some fixed number you don't know. You will typically get this kind of an expression, and your goal is to write it in this form. And then whatever is r is your magnitude, and whatever is your phi is your phase. So if, for example, my x of e to the j omega was, let's say, equal to absolute value of omega e to the minus j 3 omega. Well, this is already in that form that I talked about. What it says is that your magnitude, so my x of e to the j omega absolute value, the magnitude is equal to absolute omega as a function of omega. So I get this plot up to, of course, for omega less than or equal to pi. And the phase plot is simply, when we say draw the phase plot, that is just asking to plot this e to the j, whatever is the phi expression. So what is that phi expression? It is minus 3 omega. So x of e to the j omega is that, the phase of that is minus 3 omega. So the plot that you get for that is just this straight line with a slope of minus 3 as a function of omega. And what this plot is saying is, for every little omega, you can find out what is the Fourier transform as a complex number, what is the magnitude of that Fourier transform, or what is the phase of that Fourier transform for that particular value of little omega. This question is about one of the practice exam problems, and the problem is asking that you are given x of t, and it has a Fourier transform which is a box function. Let's call it, it's up to omega m to minus omega m and height of 1. So this is the Fourier transform x of j omega. And you are given now y of t, which is x square of t. And you are asked find y of j omega. Well, the answer to that basically depends upon the property of the Fourier transform. So to find that, I just write x square of t is x of t multiplied by x of t. Now, remember the property that if you multiply in time domain the Fourier transform, so the Fourier transform of x of t multiplied with x of t, what is that equal to? So that is simply equal to 1 over 2 pi Fourier transform of x of t convolved with Fourier transform of x of t. Okay. So that is 1 over 2 pi x of j omega convolution with x of j omega. And I hope that in your linear systems you did enough exercise of convolving two box functions. If you did not, then you should just use the definition of convolution to prove that what you get is just a triangle. The convolution of boxes is a triangle. Okay? And the maximum of the triangle is when both the triangles are exactly on top of each other. So you can do that simple convolution exercise if you have forgotten that, but that's how you get the solution, that what you get out is a triangle And the endpoints of this triangle will, so depending upon where it started, the endpoints of this triangle will not be omega m. This whole width will be 2 omega m. Actually, I started with 2 omega m. So in this case, it will be 4 omega m. So you can do it explicitly using the convolution formula. So in one of the problems in quiz, I had said something to the effect that x of e to the j omega equals to sine omega cn over pi n. And I had asked if this is this a valid discrete time Fourier transform? Now, in this case, actually, it is much easier to see that this is not, because it is not even a function of little omega. It's a function of n. I had obviously made a typo. The correct thing I should have asked is this omega c, which is some constant times omega over pi omega, is this a valid discrete time Fourier transform? And you don't have to be given the time domain function. This is an invalid discrete time Fourier transform. This function can never be the Fourier transform of any discrete time signal. So since this discrete time Fourier transform is not a periodic function of little omega, this cannot be a valid Fourier transform. Anytime you do any calculation and your Fourier transform solution comes up which is not periodic, you ought to know without even doing anything that you have made an error, because that's the fundamental property of discrete time Fourier transform. You have periodicity in little omega.